Hello, Calculus 12 students, and welcome to the second part of related rates. Now that we've finished the introductory video, we're going to go ahead and actually work on related rate problems. So let's start off with question number 2. For question number 2, I have a circle, and the circle is increasing in area at the rate of 16 pi inches squared per second. And I want to know, the question is, how fast is the radius increasing? And we want to know that when we want to know how fast the radius we want to know how fast the radius is increasing when it has a value of 2 inches. Okay, so since we're trying to find how fast the radius is increasing, basically what that means is we're trying to find dr by dt. Okay, so dr by dt tells you how fast the radius is increasing with respect to time. And we want to find this when the radius is equal to 2 inches. Okay, so that's that part right there, right? So we want to find dr by dt when r equals to 2. And what other pieces of information are we given? Well, if you look at the very first sentence here, the circle is increasing in area at a rate of 16 pi inches squared divided by seconds. Okay, so we're given that the area, dA by dt, that's a rate, that's increasing at a rate of 16 pi inches squared per second. Okay, so now that we've kind of gone through the problem and now that we've kind of picked apart the key pieces of information, we need to find a formula that relates the radius and the area of a circle. And hopefully everyone knows that the area of a circle will probably be the right formula for this problem. So the area of a circle is area equals to pi r squared. And what I'm going to do next is I'm going to take the derivative of this expression with respect to t, because this is a related rates problem. So let's take the derivative with respect to t, d by dt of all that. Okay, so just like in the first video here, if I have an expression like this, we just combine that, so that's going to be dA by dt. Okay, so you can just picture this a as a divided by 1 and just times all the letters together. And moving on to the second part, so if I'm taking the derivative with respect to time, you need to recognize that the pi right here, that's just a constant, right? So whenever we have a constant, and if we want to take the derivative, we just pull the constant out to the front. And now I take the derivative of r squared with respect to t, so this will be 2r, and using the chain rule, the derivative of r would be dr by dt. Okay, so there it is. There's my derivative with respect to t. Alright, so I know this expression right here, dA by dt, I know that's going to be 16 pi. So let's just plug that in now, 16 pi. Because remember, the goal is that I want to find dr by dt, and that's this part right here. Okay, so that's going to equal to pi times 2. And what's the radius? Well, the radius is going to be 2 inches, so let's just substitute that in and solve for dr by dt. Okay, alright, so dr by dt, if I isolate for dr by dt, that's going to be 16 pi divided by pi times the 2 times the 2. And once you do all the math there, you'll notice that the pi's will cancel, and 16 divided by 2 times 2 is simply going to be 4, and the units will be inches per second. Sorry about that, inches per second, so INC per second. Okay, let's move on to the next problem. Alright, so for problem number 3, I have a situation where air is being pumped into a spherical balloon. So a spherical balloon kind of looks like that, like a 3D shape there. Alright, so there's my spherical balloon, and air is being, so basically the air is being pumped in at a rate of 800 cubic centimeters per minute. Okay, so let me just kind of underline that, 800 cubic centimeters per minute. And then I want to know how fast is the radius of the balloon changing at the instant the radius is 30 centimeters. Okay, so for this question, I want to know how fast the radius of the balloon is changing. So that's going to be, I'm looking for dr by dt again. And basically I want to find how fast the radius is changing with respect to time when the radius has a value of 30 centimeters. So this is when r is 30 centimeters. Okay, and what do we know? Well, let's go back to the beginning of the problem here. We know that air is being pumped. So air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. Okay, so all that information right here highlighted in that black circle will tell us what we know. And since air is like a type of volume here, and we know it's a volume because we have cubic here. So cubic is like centimeters cubed divided by minutes, cubic centimeters per minute. So that's going to represent your volume. dV by dt is going to equal to 800. Okay, so I just want to highlight this centimeters cubic centimeters. That's going to match your volume, and this minutes right here will match your time. Okay, so now we need to find a formula that will relate, the radius of a sphere and the volume of a sphere. And going back to your grade 10 notes, the volume of a sphere is 4/3 pi r cubed. All right, so let's go ahead and take the derivative of this with respect to time. So if I do that, that's going to be dV by dt. Okay, and this part right here, this 4/3 pi, that's just a constant. So whenever you have a constant, let's just pull that out to the front. So this is going to be 4/3 pi, and then we got to take the derivative of r cubed with respect to t. So that's going to be 3r squared, and then using the chain rule, this is going to be dr by dt. Okay, and after that, we can just substitute our numbers in here. So what is dV by dt? Well, dV by dt is simply going to be 800. So this is going to be 800 equals to 4/3 pi times 3 times r. Well, r is going to be 30. So this r here is going to be 30, which is the 30 centimeters that's given to us at the start of the problem. All squared times dr by dt. And our goal is we want to solve for this dr by dt. Okay, so if I solve for dr by dt, mathematically, if I rearrange all the terms, this is going to be 800 divided by, well, over here, this 3 and that 3 will cancel, so basically I'm left with 4 pi times 30 squared. And if you do all the math and all the simplifying, you'll get 2/9 pi, and my units will be centimeters per minute. Okay, I'm just looking for the I'm just trying to find how fast the radius is changing with respect to t, so I don't need a squared on my units or a cubed on my units. I'm just looking for just the distance divided by the minutes. Okay, and just so that we're confident that our units are correct, I mean centimeters matches the units for radius, and minutes also matches the units for time. All right, so hopefully that's good enough for that kind of a problem. Okay, let's move on to problem number 4. Now for problem number 4, we have one of these classic ladder problems. So the top of a 25-foot ladder is sliding down, so that's going to be a key word, sliding down vertically. So it's sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of the distance between the bottom of the ladder and the wall? Okay, so before we kind of get into this kind of a problem here, let's just draw a picture here. Here's my wall, and here's my ground, and here's my ladder in red. So this is my ladder, and my ladder is 25 feet long. Okay, now the question states that, I'll highlight this in green again, it says that the 25-foot ladder is sliding down a vertical wall. Okay, so if the ladder is sliding down the vertical wall, then what that means is that if I label the vertical side as y, if y decreases, that means the bottom of the ladder, it should shift to the right hand side. So if this whole ladder that I'm highlighting in the down direction here, if that goes down, then hopefully you can see that the bottom right hand side will actually move out further to the right. So what that probably means is, basically what I'm trying to say is if y decreases, then x will increase in the right direction. Okay. Okay, so let's go ahead and now collect some information here. It says that the 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. So since we're falling down, we know that we're given that dy with respect to time is actually decreasing. So I should have a minus sign here, and I can label this as 3 feet per minute. Okay, so y is falling at a rate of 3 feet per minute. So dy by dt is -3. Okay. And then basically for the rest of the problem, we want to find what is the rate of the distance between the bottom of the ladder and the wall. So what is the rate of the distance between the bottom? So here's the bottom of the ladder and the wall. Here's the wall. So basically what we want to find, if we want to know how x is changing. So we're trying to find what is dx by dt. Okay. And we also want to know dx by dt when y equals to 7. Okay, so 7 feet. And that's just right here. Okay, great. Now, just by looking at this picture, we have dy by dt, dx by dt, and I need a formula that will relate the x and y values here and this 25-foot ladder. So hopefully you can see that the formula that will relate all of this is actually the Pythagorean theorem. So that's going to be x squared plus y squared equals to, well, it's going to equal to 25 squared. So there it is. There's my Pythagorean theorem there. And basically from now on, just like the other previous problems, I need to take the derivative of that expression with respect to t. So that's going to be 2x times dx by dt plus 2y times dy by dt. And this 25 right here, well, that will never change because the ladder is 25 feet long. So the derivative of a constant is going to be 0. Now, when I look at this expression right here, the goal is I want to find dx by dt. I definitely have the y value here highlighted in blue. That's going to be 7 feet there. 7 feet. And I also know what dy by dt is. This dy by t highlighted in green there, that's going to be -3. The problem is that I don't know what this purple x is, right? X, I don't know that x. So what we need to do is we need to go out there and find what x is. And basically what that means is we just need to solve this triangle here. We want to know what x is when the ladder, well, the ladder is always 25 feet long. And we want to know what the value of x is when y is equal to 7, right? So once the ladder hits a height of 7, we should have an idea of what the value of x is. Once I solve for this x here, I can plug that back into there, and then I can go ahead and solve my problem. So let's go ahead and find this x value here. And in order to find that x, we just continue to use the Pythagorean theorem here. So 7 squared plus x squared equals to 25 squared. And if we do the math there, x is going to equal to 24. Okay, so let's go ahead now and substitute 24 in. This is going to be 2 times 24 times dx by dt plus 2 times, well, y is 7, and dy by dt is going to be -3, and that's going to equal to 0. Alright, now the goal is I want to solve for dx by dt, so this is going to be dx by dt equals to 2 times 7 times +3 now, because I bring this whole expression to the other side, so that's going to be positive, all divided by 2 times 24, and if I do the math there, I get a final answer of 7/8, and this is going to be feet per minute. Alright, and there you go. Let's move on to the next question now. Alright, so for problem number 5, I have a right circular cylinder, and that's this whole thing over here, highlighted in yellow, and it's changing shape. Okay, the radius is decreasing at a rate of 2 inches per second. Okay, that's a key word, decreasing. So that part there highlighted in red, now that we've done a few problems here, that's going to be dr by dt, and that's going to equal to -2 inches per second. Okay, and then it says while its height is increasing at a rate of 5 inches per second. So that's going to be that expression right there highlighted in blue. That's probably going to be dh by dt equals to 5 inches per second. Okay, so when the radius is 4 inches and the height is 6 inches, how fast is the volume changing? Okay, so it looks like this cylinder right here, it looks like the radius is getting smaller, so the sides are getting smaller, and the height seems to be getting bigger. Okay, so let's go ahead now and just collect some information here based on the problem. So we are given, so we know that dr by dt, we know that's going to be -2 inches per second. I also know that dh by dt is going to be 5 inches per second. I also know that the radius is going to be 4 and the height will be 6 when all this is going on. Okay, so there it is, radius of 4 and a height of 6. Okay, so let me just highlight those, highlight that, highlight that. Okay, so going back to my diagram right here, this is my right circular cylinder here. Well, in order, basically what we need to do now is we need to find a formula that will relate the, something that will relate the radius and the height of this object here. And since we're trying to find how fast the volume is changing, we probably need the formula that we probably need is the volume of a cylinder here, and that's going to be, well, the top will be pi r squared, that's the area, and we just times that by the height in order to get the volume. So the volume of this object is pi r squared times h. So that's the formula that will connect the volume, the radius, and the height for this problem. Okay, sorry, lots of stuff there. Okay, so let's go ahead and write this down. Volume is pi r squared times h, and now we're probably getting the hang of this, and we need to take the derivative of this whole expression with respect to t. So this would be dv by dt equals 2. Well, this pi right here, that's a constant, so I'm just going to pull that out to the front. What's the derivative of r squared? Well, that's going to be 2r times dr by dt, and then I need to times that by h, plus hopefully you guys recognize that this is going to be the product rule here. Right? And I'm going to put a whole bracket around here because I pulled that constant out. Plus r squared. And what's the derivative of h? Well, that's going to be, well, the derivative of h is 1 times dh by dt. And let's close that off. Alright, after this, let's go ahead now and plug in the numbers now, because our goal is we want to find what dv by dt is. So let's just substitute the numbers here. This is pi, this is 2 times, well, what's r here? Well, this r right here is this r right there, so that's going to be 2 times 4. And what is the next expression here? What is dr by dt? Well, dr by dt, if we go back up, it's this guy right here. It's -2. So this is going to be -2. And my height here, once again, given my problem, is going to be a height of 6 plus r squared. That's going to be 4 squared. And this 4 right here and that 4, they're the same. And dh by dt is going to be 5. Okay, so if you're not sure how we got this blue 5 there, let's just go back up again. And that's this part right here. dh by dt is 5 inches per second. Okay, and once we do all the math here, this is going to be pi. Actually, hold on. Now, let me just delete all this. If you go ahead and do all the math here, you should get -96 pi plus 80 pi. So that'll give you a value of -16 pi inches. Okay, sorry, not sin, but inches cubed per second. And the reason why it's cubed is because you're solving for dV, right? You want to find out how the volume is changing, and volume will always have a cubic meter in there. Okay, so the way you kind of read this is that the volume of the circular cylinder is decreasing at a rate of -16 pi inches cubed per second. Okay, let's go ahead and go on to the final problem here, problem number 6. Now for problem number 6, there is a small little error. Can you please just delete this extra 1 there? Let's put a dot there. We don't need that. We do not need that extra 1 there. Okay, so for this problem, we have an inverted cone and it's leaking water at a rate of 1 centimeter cube per minute. The cone has a height of 9 centimeters and a diameter of 6 centimeters. The question states, find the rate at which the water level is dropping when h equals to 3 centimeters. Okay, so as of now, we have this cone and it has a height of 9 centimeters. And it has a diameter of 6 centimeters, meaning that the radius here is going to be just 3 centimeters. Okay. All right. So what else do we have for this problem? Well, I want to find the rate at which the water level is dropping. Okay. So I want to find the rate at which the water level, keyword water level. So that means we're probably solving for dH by dt, water level with respect to time. And we want to know this when the height is 3 centimeters. Alright, and the final thing we have is this part at the beginning. The cone is leaking water at a rate of 1 centimeter cubed per minute. So since we have that cube there, that means I'm dealing with volume again. So this is going to be dV by dt. We're given dV by dt, which is going to be -1 centimeters cubed per minute. Okay, so once again, whenever you see a cube there, that probably means your numerator will be something that has to do with volume. Okay, and the good thing about this question is we're given this formula here. So we're given that volume equals to 1/3 pi r squared times h. Now, with all the previous problems, we probably have to go ahead and find the derivative of this expression. And what I'm going to do right now is I'm going to pause it and I'm going to allow you guys to find the derivative on your own. And then let's compare what we have. Okay, so after I've taken a few seconds there to take my derivative, this is what I have. And with like all the previous problems, if you've taken the derivative, like the previous problems, if you've taken the derivative, the next step is you want to substitute the values that you are given into your equations and solve for the missing unknown. Now the problem is that I have this dr by dt, okay? And based on the information that's given to me, I don't have anything about dr by dt. So basically what's happening is that we have a problem because we've taken our derivative. We've taken our derivative correctly, I believe. But the problem is if I do take the derivative, I get dr by dt. And unfortunately, I don't have any information in this problem for dr by dt. I don't know how fast the radius is changing with respect to time. Okay, so what that means is I have a problem and I need to go back and think about another solution to this problem. And the key thing here is I have this value of r here. And as long as that r is there, and if I take that derivative, I will always get a dr by dt value. So what I need to do is I need to eliminate that r. Okay, and this is how you eliminate the r. Going back to your little diagram right here, hopefully you can see that we have a triangle here. And let me just redraw this triangle on the side here. Okay, so this has a horizontal distance of 9 and a vertical distance of, that has a horizontal distance of 3, and then we have a vertical distance of 9. What we can do is that we can create a similar triangle right here so that we can relate the radius and the height. So this is some random value r for that radius, and for this distance right here in black, we'll call that h. Okay, so this is a similar triangle because both of these triangles share the same side, and they also share the same angle. Okay, so using similar triangles, the relationship is I can take my 9, which is this value right here, and I can divide that by 3, which is my radius there, and I can match that up with my other fixed values of r and h. So let's just match the heights with the heights and the radius with the radiuses. So this is going to be 9/3 equals to h over r. Okay, so if this is going to be my radius, then that will be my radius of my smaller triangle. And if I go ahead and solve for r here, by rearranging the terms here, this is going to be 3h divided by 9, which is going to be h divided by 3. Okay, so this is what r equals to. R is h divided by 3 by similar triangles. Now, if I go back to my my regular problem here, let's go ahead and substitute that in for r now. So this is going to be volume equals to 1/3 pi Now r is, I can change r into h over 3 now. Divided by, h divided by 3 all squared times h. Now go ahead and simplify this. So this is going to be volume equals to 1/3 pi times h squared divided by 9 with the h. And then I'm going to take my 9 and my 3, I can multiply that together. So this is going to be volume equals to pi divided by 27 times h to the power of 3. Okay, now let's go ahead now and take the derivative, because this expression right here seems pretty easy to find the derivative here. So this is going to be dv by dt equals to, well, this part right here is a constant, so constants we can leave outside. That's pi over 27. So this is going to be 3h squared dh by dt. Alright, now after that, let's go ahead and just plug the numbers here. This part right here, dv by dt, that's going to be -1. So this is going to be -1 equals to pi divided by 27 times 3 times h squared. Well, this h right here is going to be this h right here. So let's plug that in. So that's going to be 3 times 3 squared times dh by dt. Okay, and our goal is I want to solve for dh by dt, and I'm multiplying by everything in here. So once I do all the math here, this is -1 equals to pi divided by 27. This right here is 3 times 9, so that's going to be 27 as well, times dh by dt. And after you do all the math and move all the terms, dh by dt is going to be it's going to be -1 over pi centimeters per minute. And that's my final answer. Thank you very much.